Hello. Today we're going to talk about Query Optimizer in Cloud Spanner, query plans, and how to manage the Query Optimizer behavior. My name is Vlad. I'm a technical lead on Cloud Spanner working on SQL queries. In this presentation, we'll talk about Query Optimizer in Cloud Spanner, what kind of problems it solves, and the challenges it has. We'll then talk about stability of query plans and the ways user can control optimizer behavior. Let's start with a quick overview of what the Query Optimizer is. SQL is a declarative language. Unlike languages like Java, it describes the intent. It describes what data the user wants to get from the database. Query Optimizer translates this intent into a series of steps that the execution engine can then follow when executing the query. So let's look at a simple example. We're going to look at a query that selects a set of unique names of all rows in a table accounts. We can see the query plan by going to Cloud Console and running the query in the console. It will display the query plan in the explanation tab. There are a few interesting things that we can see in the query plan. First of all, we can see this distributed union operator. This is a unique operator to Cloud Spanner because Spanner is a distributed database. Cloud Spanner uses range partitioning and it splits the data into chunks that we call splits. A single query can read data from multiple splits, and this is exactly what happens in this query. When the query reads data from multiple splits, Spanner will send a subquery to each split that may contain the data that we are seeking. In our case, this query will be distributed to all the splits on an index of accounts table. And this is exactly what the distributed union operator does. It will send subqueries to all the relevant splits. The operators that we see below distributed union are the operators of the subquery that run on each split. The subquery will scan an index, accounts by name. It will scan an index on name, and then it will remove duplicate names from the data. The query uses an index rather than reading from the base table in order to make the query streamable. The results from each subquery, from each split, are then combined together on the root node by the distributed union operator, which also has to remove duplicates of names between splits. So each subquery removes duplicate at a split level, but there can still be duplicate names across splits, and those duplicates are removed in this operator. In this example, the example that we just saw, the decisions that the optimizer made were pretty simple. But this is not always the case. There are many queries where the optimizer has to make decisions that are not obvious. Let's look at a relatively simple example. We have a query that returns account ID and age from the accounts table for all accounts where the name matches some parameter P. The key of the accounts table is ID, and we have an index on the name column. The accounts table also has an age column, which is not stored in the index. So there are two possible plans for this query. The base table plan will scan the entire accounts table. It will then filter out rows that have a name that doesn't match parameter P, and will return the results to the client. The index plan, on the other hand, will scan an index by name. The index by name will will give us all the account IDs corresponding to the name that we are seeking, but this is not enough. The query also requests an age, which is not stored in the index. So how can we get the age? To get the age, we have to join the results from the index with the uh, base table accounts, which is what happens here. So both plans will yield exactly the same results, but which plan is better? Apparently, this depends on a parameter. If a if name that we're seeking represents a value, corresponds to a value that is not very common in the table, the index plan is much better. At the same time, if P represents a value which constitutes majority of the rows in the table, the base table plan is better. This is because it's cheaper to sequentially scan a table than to join two tables together. So how does the optimizer makes the decision of which plan to use? The optimizer uses statistics to guide its decisions. In our example, the main part of the statistics will be the number of rows and number of distinct values for each column. For example, in the accounts table that we just saw, we have 45,000 rows. The ID column has also 45,000 distinct values because it's a key. The name column has two distinct values, Alice and Bob, and the age happen to have three distinct values. The optimizer uses statistics, and in most cases, it will pick the best available plan. At the same time, sometimes the optimizer will pick a suboptimal plan. This usually happens when the statistics is either not up to date. For example, if the user inserts a lot of data into the database and the statistics hasn't refreshed yet, or if there is a large data skew in the statistics, if there is a large data skew in the data that the statistics does not represent. For example, name equal Bob in our previous example is a simple example of such data skew. Users can mitigate the cases when the optimizer selects a suboptimal plan by injecting query hints. For example, force index hint tells the optimizer which index to use, and the optimizer will use this index regardless of its cost estimates. Usually, the query plan that the optimizer selects will be stable over time. But this is not always the case, though. Sometimes the query plan may change, even though the application stayed the same and the query hasn't changed. The two main reasons that the query plan can change are updates to the query optimizer and changes to query statistics. In most cases, such changes to the query plan will actually improve performance of the query. But in some very rare situations, the query may flip to a suboptimal plan. From a user perspective, this will manifest as a performance regression. In some very extreme cases, this can even be orders of magnitude regression. In this presentation, we'll talk about why it happens and how Cloud Spanner users can mitigate this risk. So we talked about the two reasons that the query plan may change, and one of those reasons is updates to the query optimizer. Cloud Spanner is a managed service, and internally, we continuously roll out updates to Cloud Spanner binaries, and the databases always use the latest binary. The query optimizer is a bit more sensitive because it has a lot of heuristics. And because of this problem of potential changes to query plans, we decided to ship improvements to query optimizer in a slightly different way. We update Query Optimizer in discrete versions that we publish. We ship those updates about every 6 months. Each the Cloud Spanner embeds all of the optimizer versions. So users can choose which optimizer version they would like to use for queries. By default, all queries will use the latest optimizer version, but this can be controlled, and we will see how to do it in a few minutes. The optimizer statistics behaves in a very similar way. A new optimizer statistics is collected every 3 days. Each new statistics we collect is stored separately in what we call a package. Spanner keeps 30-day worth of last statistics packages. So we collect statistics every three. So since we collect statistics every 3 days, users can expect about 10 statistics packages at any point in time. Like with optimizer version, by default, queries will use the latest statistics package and will automatically switch to the latest package when a new one becomes available. And similarly to optimizer version, users can control and can choose which statistics package they want to use for their queries. So we said that users can control optimizer version statistics. Let's explore how to do it. There are 3 ways that Spanner provides. The first option and the first option is the simplest and the most commonly used, and it is through database options. Users can change database option that will set the default optimizer version or default statistics package for all queries. The other option is to use query hint at a query level. With a statement level query hint, the query can specify which optimizer version or statistics package we want to use for that particular query. This is especially convenient for testing and experimentation in Cloud Console. Users can run the same query with different version and different statistics, and can explore how it affects runtime performance and how it affects the query plan. We also provide an option to choose the optimizer version and statistics package through client-side APIs. The syntax is slightly different in every language. And we also have an environment variable that users can set on a client process, and it will also choose the default optimizer version or statistics package. So how do we recommend to use all this? First of all, for the most important and mission-critical queries, we recommend using query hints to avoid any potential regressions in the query plan. For vast majority of the queries, most users will choose to be reactive. In the rare case of a regression due to query plan flips, users will pin the database to an older optimizer version or an older statistics package, and this way users can quickly mitigate a regression. The other approach is a proactive one, where users pin optimizer version and statistics package to one that they know that works well, and then users would then regularly test their application with the latest optimizer version and statistics package, and will move the production settings forward after the testing has been done. This is the safest option, but it requires an ongoing effort. So to summarize, we recommend annotating a handful of the most critical queries with query hints to avoid any potential regressions in query plans. We also recommend to users to familiarize with DDL statements that pin the optimizer version and statistics to the last known good version. so that users can quickly mitigate regressions if they happen due to query plan flips. And lastly, we also recommend users to test new optimizer versions before they get enabled by default. If users detect any performance regressions, they can rewrite the query or temporarily pin the optimizer to an older version, thus avoiding regression when the new optimizer becomes enabled by default. Thank you for listening.